Okay, so we know whenever we have an acidic or basic solution, we can measure how acidic or basic something is by looking at its pH. And the pH of a solution depends on the fact that water is amphoteric. If I have pure water with nothing else in it at all, absolutely 100% pure water, what we find out is that the water will self-ionize, which means one H2O molecule will act like a base and the other will act like an acid. And we'll get this equilibrium set up, where we have hydronium and hydroxide. Now we know that water is neutral, so the same amount of hydronium and hydroxide exists to make water neutral. When I write the equilibrium expression for this, since this is liquid and this is liquid, I would get a K that looks like this. Okay, this K is specifically called Kw because it relates to water self-ionizing. And at 25 degrees Celsius, the K value is 1 times 10 to the negative 14th, and that's equal to the concentration of hydroxide times the concentration of hydronium. Now, since it's hydronium times hydroxide equals 1 times 10 to the negative 14th, we know that the concentration of hydronium must equal the concentration of hydroxide, because that's what this equation tells me. There's a 1-to-1 ratio. So each of those is equal to 1.0 times 10 to the negative 7th moles per liter in solution, which we'll get back to in a minute. Okay. So when we're looking at acids, and we really do everything in terms of acids, concentration of hydronium in different acids can be anywhere from 10 molar to 10 to the negative 14th molar. And that's a pretty wide range of powers of 10, because this would be 10 to the first, 10 to the negative 14th. That's a range of 10 to the 15th. So a more convenient way to express the concentration of hydronium is the pH scale. So when we look at the pH scale, pH is equal to the negative base 10 log of the hydronium ion concentration. So if I know my concentration of hydronium, I take the negative log of that and I get the pH. If I know the pH and I want the hydronium concentration, I would just take the anti-log of this equation, which gives me hydronium equals 10 to the negative pH. So if I have pH and I want hydronium, 10 to the negative pH. And this is very useful for dealing with very small numbers. So you're going to see this application applied in other places. So we can talk about POH, which would be the negative log of OH minus. We can talk about PKW, which would be the log of KW. So now thinking about the KW expression, Kw is the concentration of hydronium times the concentration of hydroxide. Taking this negative log idea and applying it to this equation tells me that pKw is equal to pH plus POH. And pKw has a value 1 times 10 to the negative 14th. So pH plus POH, if I take the negative log of 1 times 10 to the negative 14th, I get 14.00. Okay, so this is a very useful relationship when we go to solve questions. Okay, the pH scale itself. The pHs that we deal with, pretty much we think of 1 to 14. But really, you can have 0 pH. 1 molar HCl has a pH of 0. You can have negative pHs. You can have pHs above 14. It just matters what the concentration of hydronium ion is. But what we find is that for most of the weak acids and bases we deal with, we're dealing with pHs somewhere between 1 and 14. So that's why we typically think of the pH scale as being from 1 to 14. So you can see pure water is neutral. Now you'll notice the pH is equal to 7. So that means the concentration of hydronium ions is equal to 10 to the negative 7th, or 1.0 times 10 to the negative 7th molar. So if I have a whole number pH or POH value, and actually I guess I circled the POH, it should really be the pH. Well, actually, POH is also equal to 7, so the same thing is true for OH minus. If I have a whole number value, I simply turn that into 1 times 10 to the negative whatever. So that can also give me an estimate. Even if I have a pH that's a decimal, I can kind of estimate what the concentration should be. So let's take a look at some calculations involving pH. So the first one, I want to know the pH and the POH of a 1 times 10 to the negative 3rd molar hydroxide ion solution. So I know that POH, this is the way I'm going to do this, is equal to the negative log of 1 times 10 to the negative 3rd. So the POH is equal to 3.00. Okay, just a note on significant figures. There are 2 significant figures there. When we use logarithmic scales, the significant figures are right here. That number is a placeholder. So this corresponds to just 10 to the negative 3rd. That corresponds to the 1.0. Okay, so now I know what the POH is. So to find the pH, I just go 14 equals pH plus POH, which is 3.0, so pH equals 11.00. For B, I have a 1 molar solution of H+, so pH equals the negative log of 1. So the pH equals 0, because the log of 1 is 0. So POH equals 14.00. So that's where this 14 equals pH plus POH will come in handy as we try to convert from POHs to pHs and back and forth, rather than dealing with exponents. And that really is the point of the pH scale. Okay, let's look at one more question. This one says, the pH was measured to be 7.41 at 25 degrees Celsius. Calculate POH, H+, and the OH minus concentrations. So I know pH equals 7.41. POH must equal 14.00 minus 7.41, which equals 6.59. So the concentration of H+, which is really the concentration of hydronium, which is what I'm going to use, is 10 to the negative 7.41, which equals 3.9 times 10 to the negative 8th molar. The concentration of hydroxide would be 10 to the negative 6.59, and that equals 2.6 times 10 to the negative 7th molar. So I think this is easier than trying to plug numbers into the kW expression directly, and it makes the math a little easier. Okay, so now the last thing we're going to look at is the pH of strong acids, because next time we'll look at the pH of weak acids in much more detail. So the pH of a 0.1 molar nitric acid solution, I know that it's a strong acid. So when it goes into water, it's a left to right reaction. I'm going to get nitrate plus H3O plus, pretty much 100%. So the pH is going to be equal to negative log of 0.1. So that means it's going to be 1.00. For B, the pH of this 1 times 10 to the negative 10th molar HCl solution, pH of that solution is going to be equal to the negative log of 1 times 10 to the negative 10th. So the pH is going to be 10.00.